Okay, before talking about integrals, we're going to first stop and talk a little bit about sums. So, you'll remember from the last video that this is the integral. But sums don't have to be this complicated. We can have simpler sums like that. So we're going to learn how to evaluate these simple sums before we talk about integrals. If you're in AP Calculus AB, this is the last time you'll see sums, but if you're in BC, they'll come back when we talk about infinite series. All right, there's 4 sum formulas you have to know and some characteristics about sums. So the first formula is the constant sum rule. Right? So if you're summing n terms of a constant, this is the same as going c plus another c until you have n c's. What is this like? This is multiplication. So we just write this. This is equal to cn, right? It's pretty straightforward. The second formula is the sum of a first degree term. Something like this. And so this is equal to n times n plus 1 divided by 2. The most famous example of this is the sum of 100, or sum to 100. So consider this. This is equal to 1 plus 2 plus 3 plus, so we get 2, plus 98 plus 99 plus 100. So if you notice, if we work outside in, this plus this is 101. These two add to 101. These two add to 101, and so forth. But how many 101s do we have? Well, we have 50 101s because every time we make a pair, we use 2. And since there's 100 numbers here, there's 50 pairs. So that's why we have, so this is here, n, the 100, times n plus 1 is 101, divided by 2, which is 50 101s, which is 50-50. Right? So it's a cool example proof that I really like. And it's a good way to see why this rule works. The third formula is when you're summing a square. Like this. And this is equal to n times n plus 1 times 2n plus 1 all over 6. And lastly, this one is for summing a cube. Like here, this is n squared times n plus 1 squared over 4. And you'll notice that this is this squared. Right? So the proof for this is pretty long, but that's just a cool relationship between the two. We're going to talk about some properties of sums. And the most important thing to know is that a sum is a linear operation. So this lets us do stuff like, here, we'll let a of I and b of I be sequences, because when you're doing a sum, you sum according to a sequence, which is whatever is inside. So we can do stuff like, if we have a constant times a series, or a constant times a sequence, we can pull out the constant outside the sum, and the series is still the same. We can also, like limits and derivatives, we can split sums into multiple sums. Right, so if we have something like this going on, we can split it into. So the four formulas that I mentioned in the last clip and these two properties of sums are pretty much what you have to know to evaluate most sums in AP Calculus. Okay, now we're going to talk about integration. Probably the biggest thing you have to know about integration is that integration is the reverse of differentiation. Right, so these two undo each other. So if we have a function, right, and we take the derivative, right, we go down one rung down the ladder of derivatives, the integral of the derivative will bring us back up to the function. So knowing these two are opposites of each other will be really helpful in the next chapter when we solve differential equations with integration. But this is why an integral is often called an antiderivative, because again, the integral undoes the derivative, making it an antiderivative. The indefinite integral of a function gives us another function, but there's something missing here. To show you this, I'm going to let big f of x just be any function. Like, how about 3x squared minus 2x? Well, the derivative of this, and because integration is the reverse of differentiation, that means differentiation is the reverse of integration. So if I take the derivative of this, I should get f of x back. So small f of x is 6x minus 2. But what if big f of x equaled 3x squared minus 2x plus 6? If I take the derivative of this, it should get me f of x, which it does. But notice, there's two possibilities of what big f of x could be, but they both differentiate down to the same original function. So how do we account for this? We add a constant of integration, or plus c, after every indefinite integral, because of the fact that the derivative of a constant is 0, and so there's no way to know which of these this is coming from. So we have to add this constant to ensure that we're taking care of all the possibilities of the antiderivative. This is what's known as the family of antiderivatives for this original function, little f of x. But we'll get more into that in the next chapter of differential equations. Now that you know what an indefinite integral is conceptually, now it's time to learn how to actually find it. Since we know a lot of derivatives already, we're going to know a lot of integrals. So we'll start with the integral of 0. Now, if you remember, the derivative of a constant is 0, so the integral of 0 must be a constant. And notice that this is the constant of integration, or plus c, which follows with every integral. Second rule is integral of a constant. I'll call k. Remember how the derivative of a linear term is just its coefficient. So the integral of this coefficient is a linear term. followed by the constant of integration. The third rule, probably the most important rule, is the integral of a polynomial. So remember how when we differentiate a polynomial, we multiply by the exponent and drop the exponent by 1. So to integrate, we do the exact opposite. We increase the exponent by 1 and then divide by the new exponent, followed by a plus c. You're starting to see the pattern here. Whatever we do to differentiate this, we just do the exact opposite for integration. And here are all the integration rules written out, if you want to copy them in a notebook or something. Some notable integration rules. Notice this change to the power rule. We can't use it when n is -1, because -1 plus 1 is 0. You can't divide by 0. So when this happens, we use the ln rule, right? Because the derivative of ln x is 1 over x. So the integral of 1 over x is ln x. And also notice the integral of e to the x is still e to the x. We're going to close out the video by going over properties of integrals, and then we're going to do some examples. So the first property, well, actually before all this, so like limits, derivatives, and sums, integrals are also linear operations. So, like limits, derivatives, and sums, we can pull out constants, and we can split integrals. Like so. Okay, I'm going to do 2 example problems. First one is the integral of x to the 4th minus 3 sine x plus 1 over x dx. The second is the integral of e to the x minus secant squared x. Let's start with the first one. So right away, let's break it into 3 integrals so that we kind of see easier what's going on. So let's do the like this. So we split into 3 integrals. And now let's take the 3 out from inside the integral, move it outside. Like this. And now we can evaluate each of them one at a time. So here, using the power rule for integrals, we have, this is 1/5 x to the 5th minus, the integral of sine is negative cosine, but that minus cancels this minus, so this becomes a plus 3 cosine of x. And remember, we can't use the power rule here. We have to use the ln rule because you can't divide by 0. So this is ln of x. And don't forget the plus c. Right. Now for the second example, again, I'm going to split into 2 integrals. Like this. And again, we can evaluate them one at a time. So remember, the integral of e to the x is itself minus, now the integral of secant squared x is tangent x. And of course, don't forget the plus c. So there you go. That's indefinite integration.